The first time I heard about LQR, which is linear quadratic regulators, I thought it was one of those scary control theory terms that are just there to intimidate students. And I'm not even going to lie. Part of me thought if I just mentioned LQR in my bachelor's thesis, maybe I'll get a better grade. It sounded advanced, mathematical, and impressive, like something only serious engineers would be using. But when I started to actually use it in the project, I realized something. It's not impressive because it's complicated. It's actually impressive because it's simple and honest. LQR forces you to answer one very simple question: what do I actually care about? For most of us, the first controller we learn is PID. You measure error, you multiply it by a proportional gain, and you could add an integral term or a derivative term or both. And then you tune the gains until the system behaves nicely. And to be clear, PID works extremely well in many situations. But here's what's really happening with PID. You're tuning behavior. If it reacts too aggressively, you lower the gain. If it's too slow, you increase the gain. You're just adjusting knobs until it feels right. What you're not explicitly doing is defining an objective and solving it optimally. LQR starts from a completely different mindset. It asks, do I care about the state error? And do I care about the energy required to control the system? Because control effort is not just some abstract number. It's motor current, it's battery drain, it's heat, it's stress on hardware. It's real physical energy flowing through your system that you might genuinely need to control. In my bachelor's project, this was not theoretical. We were working with motors powered by a battery. If we pushed too much current into those motors, we risked overheating them. We risked damaging components. So we had to care about energy, not just stability, not just tracking the error, but tracking the energy. And this is exactly why we used LQR. We made the cost of using too much control effort very high. In other words, we told the controller, error matters. But excessive energy matters a lot too. And once we did that, it worked beautifully. The system became stable, smooth, and efficient. Here's the core idea of LQR. Instead of tuning gains directly, we define a cost function. Over time, we add up two things: how far the system is from where we want it to be, and how much control energy we're actually using. Mathematically, that cost is written as an integral over time. It includes a term for state error and a term for control effort. There are two main tuning matrices inside this formula. Q tells the controller how much we care about state errors. R tells the controller how expensive control effort is. If R is large, using energy is expensive, and the controller will be smooth and conservative. If Q is large, being away from the desired state is expensive. The controller will fight harder to reduce error. You're not tuning behavior blindly, you're defining your priorities. Now, here's the elegant part. We define this cost over infinite time, from now until forever. This sounds like an impossible optimization problem, but the solution turns out to be shockingly simple. The optimal control law is just U equals minus k times x. That's it. The input is just what the value of the state variables are times some matrix and the negative of that. You just measure the state, multiply by matrix k, and apply that as the input. And somehow inside that matrix k is encoded the solution to an infinite time optimization problem. It already knows how much you care about energy, and it also knows how much you care about the error, and it balances both automatically. Behind the scenes, LQR solves something called the Riccati equation. The first time you see it, it looks intimidating. But conceptually, it does something very intuitive. It calculates the true long term cost of being in any state. It gives you a matrix called P, and the expression x transpose px tells you something super powerful. If the system is in this state right now, how expensive will it be in the future? So P is like a map of future cost. Once that map is known, computing K is straightforward. K translates future costs into present action. If a certain state leads to high future costs, the controller reacts strongly. If correcting something would require too much energy relative to its benefit, it reacts more gently. It is constantly balancing performance and energy in a mathematically optimal way. With PID, you tune gains until it feels stable and smooth. With LQR, you define what matters and let mathematics derive the best possible feedback law. PID is heuristic tuning. LQR is optimal design. That is the philosophical shift. Imagine a drone trying to hold altitude. If altitude error is very expensive, the controller will react strongly to deviations. If battery life is critical and energy is too expensive, the controller will avoid aggressive thrust changes. It will settle smoothly instead of violently correcting every small error. And it does this automatically based on how you defined the cost. The reason LQR is widely used in aerospace and robotics is simple. It turns a vague design question into a clear optimization problem. You write down what you care about, solve one matrix equation, and the final controller is just U equals minus K times X. It's faster compute, stable, and optimal with respect to your defined priorities. Of course, it has its limitations. It assumes the system is linear, it assumes you know the full state, and it assumes you care about long term behavior. But even within those assumptions, it gives you something extremely powerful, a controller that respects both physics and energy. When I first heard about LQR, I genuinely thought that it was just a fancy tool that would impress my professors, maybe boost my thesis grade. But using it in a real system changed my perspective. It was not about looking smart, it was about protecting my hardware, managing energy, and designing behavior intentionally. LQR forces you to answer a deep engineering question. How much is performance worth and how much is energy worth? Once you answer that, the math gives you the best possible controller. That is why LQR feels elegant. It's not just controlling a system, it's managing trade offs. And in real engineering, trade offs are everything. If this video helped LQR make more sense to you, then I'm really glad I was able to do my part. There's a lot more to decode: topics of engineering, robotics, science, and algorithms that shape your world. So until the next video comes out, thank you so much for watching, and don't forget to stay curious.